My name is Andor Pénzes, and I'm going to present something crazy today. And this is kind of referring to the original theme of this, this conference. You can choose your red or blue pill. But if you find the green one, then you are the chosen one, and you are the winner of this talk. So, let's imagine together a dependently typed Python. Wait, I just said dependently typed Python, so that means that did I just take both of the pills? And I kind of yes. We are just exploring this idea. How would fit the dependently typed programming into an everyday Python programming? And currently the project is in the design phase. So we are designing, we are prototyping, we are having a lot of discussion with Thorsten, who is my co-author, and who is a teacher at the University of Nottingham, and he's well-versed in dependent types. Meanwhile, I'm very well-versed in everyday programming, so we kind of try to put these ideas together. But we really would like to get an early feedback from you. So if you are interested in this topic, please come to me after the talk, and we can have a nice and fruitful discussions. Again, that's the GitHub repository, so if you want to check, then you can have these evaluators that we already have, but that's just a big mess. And we were thinking about how would we call this project, and we settled down with the DEPI. And if you are a German speaker, there is a pun there. If not, we wanted to have another one with something like as a pie, where we use the I, and actually, but that name was kind of already allocated for another project. So, but just really talk about Python and dependent types, we really have to think about what are dependent types and what is kind of the high-level idea of dependent types. And dependent types originally coming from the first-order logic, and the first-order logic Curry-Horvath corresponds to the type theory. So what you can do in first-order logic is that you can use values in your logical formulas to create statements. The same applies for dependent types. An example of this, like the vectors of length 3. So I use the 3 as a simple value in my type description. So I'm talking about the vectors of some certain length. So this is one very useful thing for dependent types, and how this is possible. It is possible because we can use types and values at the same theoretical level. They live in the same logical correspondence, in the same logical rules, so there are no distinction between them. And also, when we write a software which uses dependent types, or which kind of creates dependent types, then we have to be able to inspect the types at runtime. But that also kind of points towards the dependently typed Python, because you have to handle types at runtime. So why not to do that in Python? And also, when you implement a type checker, you have to implement a computation, a normalization in your type checker. So why not do type checking at runtime instead? So that's another crazy idea of dependently typed Python. Let's just go back to the foundations, what we do as software developers. So we write programs to actually solve problems, have some fun, or earn some money. And within these programs, we organize data. We organize information as data types. And in those data types, with those data types, we write programs, simply writing functions from transforming one data type to another data type. But sometimes these abstractions, these functions are loosey. There are some errors in them. There are kind of over-generating, under-generating problems. So what we do is we always need some external help, like unit tests, like assertions, like a type checker which helps you. But if you have a general description about how you can formalize your assertions, then kind of tells you the nicer and the unified story, and that's where dependent types really fit well for programming. And why do we even care about this? Because sometimes we want to change those programs, and whenever we change those programs, we still want to have some kind of consistent behavior. So we don't really want to lose a lot of money on a software bug. So let's see how we can do these assertions. But before we go there was a really good talk about the ADTs from Nicola. And if you haven't watched that, then I really recommend it. This is a one slide summary of that talk. And that means that whenever we write these data representation, we always try to tie things together, fields together, and those are the products. And sometimes we always want to kind of select from different options, and those are the sums. And different paradigms aim to handle this problem kind of in a different and a similar way at the same time. And in object-oriented programming, what we do, the subclasses are the sums and the fields are the products. With Haskell-like FP programming, the data constructors are the sums and the fields are the products. But this idea can be pushed further. So there is this generic programming, and the generic programming comes from this sum of products idea. But there is a nice paper from Conor McBride which talks about the levitation. And the levitation is the idea when you say that when I'm writing my programming language, my compiler, actually I should just use one data type to represent the internals and actually compile everything or interpret everything in that data type, which is also really similar to the sum of products. So I can save a lot of things from my compiler architecture, and I can easily get very, very similar things. And in the previous talk, we solved that with kind of the closure implementation of these lenses. You just said, I'm implementing this closure generally. So this is very similar to that. And Python actually already does that, because in Python, everything is a dictionary. So Python already implemented levitation, which Conor McBride said that we should do that. So that's another point for let's do dependently type Python. This is a very nice idea. Next question about compilation time or execution time. You should really ask yourself as a developer, no matter if you use static typing or dynamic typing, how much time do you wait to decide if this program is actually fine? If you do kind of JavaScript, Python, this kind of programming, you have a lot of unit tests. You have to run those unit tests, and you have to wait for those unit tests. Or you have to run your programs in different contexts and to actually understand that everything is fine. Or if you do a static checking, you are waiting for the compiler, sometimes for hours to do those checking, to do those checks for you. So there isn't kind of big debate. At the end, when we write complex systems, we have to wait. So the consistency should be really maintained somehow. And it doesn't really matter if we just put dependent types at the runtime. And that's the idea. So dependently typed Python is not a statically typed Python, but actually applied dependent types during the runtime. So assertion checking during the runtime with a nice little DSL. And let me use examples here. So I will present 3 examples. The first one is the natural numbers. And this one is just the sum of representation, sum of products representation of the natural numbers using Python syntax in this dependently typed Python dialect. So here we can say that first we create an abstract class, the nut class, or we can say that we are creating a type, the natural numbers. In this abstract class has actually 2 concrete classes. One is the 0, which represents the 0 number, and that is like the data constructor for the 0. And the other one is the successor, which has to accept one other natural number and creates a new one for us. But here there is a very important thing, is that this natural number must be checked by the runtime that the object we got here is actually fits the natural number scheme. Because this will be important in the long run of this kind of dependent typed idea. So that was the first example. The second example is the finite indices. And this finite indices, here if you can see my mouse, yes. So here we kind of introduce a type index, or index for this fin data type, or fin type, which is will be indexed by the natural number, by one natural number or by a natural number. And This is a well-known data type from the dependently type programming. So if you wrote EGDA, you are familiar with this. But this is for like something finitely indexing into some structure. But here in this syntax, we could say that we are creating a new abstract class, a new type, fin, which has one index, this n natural number. And this value must be instantiated during the constructor calls of this class. And we have two subclasses here, the zero, the finite zero, which must have an index for the natural numbers, or the finite successor, which actually accepts another finite number, and we compute its index using the index coming from the other finite natural number, and in the second line, we just wrap everything. So I give 10 seconds to consume this, and I just drink some water. And we have the last example, the typical hello world example of dependent types, the vectors. So, but in this formalism, in this object-oriented-ish like dependently type Python taste, we kind of see a little bit of new things that basically we can see the vector type as an object type, or as an object or like a class type, when we actually predefine all the operations. And here we also not just predefine all the operations that we want to have, but we also add this index that we previously had in the finite numbers. So here we define that our data type or type vector, which is indexed by a natural number, which expresses this n length of elements, n-lengthed list, basically. But we also tell that we are defining the append method or the append functionality on this type. And the append is like appending two vectors together, so that's kind of the name for it. And we expect to see another vector for the second part, the ys vector. But here, what we actually define, and where the power lies in this kind of dependent types, is that you can talk about the return type. You can talk about the value that we should have. So what kind of type should have at this return value. And the contract here, that for any append implementation, I have to say that the resulting length is actually the current length and the length of the other. So this is added together. And it's a very simple example. And here we have two different implementations for this abstract vector, and one implementation is the empty vector, which length must be 0, so that's not really surprising. But the interesting part here is how we implement the append function. Here, simply say that adding an empty vector to any other vector, just the other vector. So there is no problem, and I can write as a software developer easily. I can just implement it, yes, so return the bias as it is. But here, we have the proof obligation to actually say why we think that this is true, why this actually fulfills the contract. And here, that means that when we get the bias, we will know the type of the bias at runtime, and we can kind of inspect it, and we can slowly transform it, and we can say that we can see that originally this is the type of the bias, but we can say that actually there is a sub-expression here. We just add 0, and this is still the same natural number, and we can see that this 0 is equivalent to the self.n, and this formula is the same formula that we were expecting in the return type. So now we actually created the proof that our contract is fulfilled. And this kind of transformation could happen during some kind of constraint solving or simple normalization, or if it's not possible, we will just ask the developers and the users to provide these step-by-step derivations. And the same thing happens with the constructors. kind of the cons, sorry, not constructed, with the cons construction, that means that we are just adding one extra element for any other vector. And we just copy, the length would be +1 of this access, and we copy these fields. But to implement the append, we really have to go through this kind of Tetris. When you say that this is true, this is true. And if it's not true, then could be checked by some static checker if you want, but also it can be checked at runtime. So that's the idea, that push these assertions at runtime, but use a very nice description for these assertions. And the idea is also based a little bit on normalization, which is Thorsten's paper, and we are applying that, but I run out of time for these details. So if you are interested in that, please come to talk to me. The type system is in the making, and this is like normal research. And in the long run, we want to write the whole system, and we want to present in different conferences. So an early feedback from you would be very, very valuable. Last but not least, side effects. We are undecided, so we can say that we don't mention them in our solution because we are at runtime, and that could be bad, good or bad. You can decide. We can use monads or monad transformers to talk about it, or we can use effect handlers, built-in effect handlers like in the Unison programming language. And there will be a nice talk after this about Unison, so I would really recommend to watch that. So that's all. Thank you very much for your attention. And if there is any questions.
So you had the example with the concatenation, or sorry, the append function, and like all these like step-by-step types of the vectors, they are all equivalent just by normalization.
Yes.
So it's a bit unclear to me, like what the middle steps contribute, because it's not really step by step that they are equal. They just have the same normal form, both sides of or both ends of this.
Yes, I use this as kind of the motivating example, as an example to show that here is something going on at the type checking level at the runtime.
Oh, but wait, so are these just comments? Like, it's not like the user actually needs to...
No, those would be kind of required from the users, but we are still undecided what will be the detail which is required. So you can say that, yeah, if it's normalized the same thing, that you don't have to spell it out because we know that 0 plus x is x, so you don't have to do that. But in some cases, maybe it's kind of also used for kind of documentation, like in any other ACDA proof.
Right, and then I guess, okay, and also you might have to provide not just the endpoints, but the
sometimes the user will have to provide kind of the crucial steps.
I see.
Okay, so I have the question related to this very slide. I think the proof as you have it, the one you had there.
This one, okay.
Yeah, so I think the proof, as you have it, I think if you checked it statically, it would pass as well. And I thought the main point of having it runtime checked is that you don't actually have to write all the proofs because it can be checked on the object.
Yes.
For example, when you have like sorted dictionary, the writing proof is kind of complex thing, and you can check it at runtime that the dictionary actually is sorted. So do you have to actually write types also for this runtime checking, or?
So that's a discussion. We are still undecided how to go. It's more like, that's why I call this talk as Imagine, because we are still imagining this system.
Okay, because I imagine this would be faster if you have proof.
Yes.
But like you can check it exactly on the object that the length corresponds. Okay, thank you.
I'm wondering about two questions. Actually, one of them is how is it essentially different from, let's say, generics on values instead of on types, something like template parameters in template arguments in C++, because this seems really similar. And the second question is, could you provide a real-life example? Because like no one will write this kind of vectors, and how this can, let's say, improve developers' life in a real example. Thank you.
So I'm not familiar with the C++ template stuff, so I can't really comment on that. But I'm happy to take that offline. So the other part of the question, last year I presented about dependent types and how dependent types are kind of useful in general. And that talk was based on Idris too. And I would recommend that talk basically. But my general kind of view on dependent types, that they are nice and glorified assertions. You can provide kind of at the same level of programming language that you are using, a nice kind of DSL where you can say that this is actually how I think that this is consistent. And in Haskell, there we have GEDTs, but you will meet kind of limitations of GEDTs if you want to do something from some information from the external world. So some coming from this information coming from the external world, read from databases and so on. But last year's talk actually covers that part.